Welcome back. This is the AMAT 104 lecture videos for week 1.3. So before we start anything, just a quick reminder, do sign up for Pearson. This is where you can access homework assignments. Nothing is assigned yet, but you need to have access in order to access homework assignments. The class ID is PARK 50386. So last time we looked at many different examples of sequences, and we also have done some examples that you might see on homework assignments as well. So today let's go over chapter 9.2, that's section 9.2. And that's the linear growth model. So before we begin anything, let's define some things. So a population grows according to a linear model if in each generation the population changes by a fixed amount d. So this is a mathematical notation. And this stands for the common difference. So when a population grows according to a linear growth model, the population sequence is called an arithmetic sequence. So this is a very important term. So arithmetic sequence is just a term that defines a specific type of sequence. So in this case, we defined it from here. If it's a linear growth model. So when I say growth, this also indicates negative growth. In other words, decay. So if you see any growth or decay in a linear manner, we call it a arithmetic sequence. So let's take a look at an arithmetic sequence example. So this is the example. So let's say a city is considering a new law that would restrict the monthly amount of garbage allowed in the local landfill. So let's suppose the maximum capacity of the landfill is 20,000 tons. And currently there are 8,000 tons. In the landfill. So if the monthly maximum is 120 tons, how much garbage will there be five years from now? So before we tackle any numbers, do we all understand the problem? So in a city that currently has a landfill of 8,000 tons, is now implementing a new law that limits the garbage disposal to 120 tons. And the problem is asking, in 5 years, how much garbage will there be in the landfill? So that's pretty simple. So currently we have 8,000 tons. We have 8,000 tons. And we know that we can add 120 tons per month. So in a month from now, we will have 8,000. So in a month, we will have 8,000 plus 120 tons, which will be 8120 tons. And in 2 months, we will have another 120 added on top of here, and so on and so forth. So how would you go about calculating this? So we have seen that in this case, we're increasing by 120 each month. So in this case, 240 tons. So let's say in 2 years, how many months has elapsed? How many months are there in 2 years? So in 2 years, which is the same as 24 months, we're simply adding 120 tons on top of 8,000 ton each month. So we're doing that 24 times. So how do you do that? So if you want to do that in 2 years, we have 8,000 plus 120, and you're multiplying that 120 by 24 times because there will be 24 months in 2 years. And let's actually just calculate that really quickly. Okay, so this number actually becomes 8,000 plus 2,880 tons, and that actually becomes 10,880 tons. So this implies that in 2 years in the landfill, there will be 10,880 tons in there. So that was pretty simple, right? What if the question asks, however, though, how long? So let's say this is the second part of the question. So how long would it take the landfill to reach its maximum capacity? So what's the maximum capacity? So up here, in the problem, we have established that the maximum capacity of landfill is 20,000 tons. So we know that the maximum capacity is 20,000 tons, and it's given from the problem. So how would you go about solving this? So in order to do that, so now instead of multiplying a certain number of months, we now have the maximum capacity. We already have the number, and we're trying to find how many months it will take there. So we're simply using the same form of equation, but instead this time you have 8,000 plus, and you have 120 tons for some unknown number of months, and whatever that is, it is now 20,000. Does that make sense? So now all you have to do is to solve for n. So solve for n. So in order to do that, what do? You subtract 8,000 on each side. So that is 120 n on the left side because 8,000s cancel out. And on the right hand side, you get 12,000. And now you divide each side by 120, and you'll end up with n equals to 100. So what is this number? What is this n equals to 100? So this is the number of months it takes for this specific landfill to reach its maximum capacity from day one. So here's your answer. So let's go over some notations and facts. So a population grows linearly if in each generation the population changes by a constant amount, and let's denote D as the difference. So here, the D is actually called a common difference. Let's say common difference because it changes by the consistent amount of numbers. So this is a common difference. So let's talk about some facts about arithmetic sequence. So this is an example. That was an example of an arithmetic sequence. So when D is positive, when it's greater than 0, then we have a positive growth. Or in other words, we call this, it's an increasing sequence. And when D is less than 0, in other words, D is some negative number, then we consequently have a negative growth. And this is a decreasing sequence. But when D is a 0, it's not positive, it's not negative. We call it a zero growth. Or in other words, this is just a constant. So the notation would be you start with the P0, which in this case is the initial population. And you go over to P0 plus D. And now that's a population after one generation. So after one generation, it either increased, decreased, or it could just be constant. But we added a common difference here, so we now call this a population after one generation. And we continue this pattern as P0 plus 2D, meaning there were 2 increases of common difference, and we call that the population after second generation, so 2 generations, and so on and so forth. You go like this. And this would, since this is a sequence, this would go indefinitely, and you will reach some number ND. So what have we created here? So for any n, we can see that we can plug in some number, and in this case, this is 0, the initial population, but there's a hidden 1 here, so it's a p0 plus 1d, p0 plus 2d, 3d, and so on and so forth, and each n actually represents the population after that nth generation. So in this case, we can see that this is actually the population after n generation. And this is actually our explicit formula in this case. So remember we did an explicit formula last time. So the explicit formula for arithmetic sequence is actually given by P sub n. So this is the population after nth generation. It's given by the initial population added by the n, the number of generations, multiplied by the common difference. That's it. Then what about the recursive formula? So now we have the explicit formula. Let's look at the recursive formula. So recursive formula, as we talked about before in last class, is a formula that represents a sequence where the term depends on the previous terms in a sequence. So if you look at the difference between this one and this one, so initial population and the first generation, you notice that the only difference that you only added the d here. So going from the initial population to the first generation, what happened here is you added the common difference. Similarly, you can see that the second generation is also the same way. So to go from the first generation to second generation, you simply add another common difference. And you would simply add the common difference for each term. So we already have that established now. So we can actually create the relationship that when this is the P0 and this is the P1, because it's population of the first generation, this is P2, and so on and so forth, we can see that P1 is actually P0 plus D.
0 plus.
As well as when you have P2, it's actually P1 plus D. So what do you see here? So simply we're noticing that if given any term in each of the sequence, in the sequence, you simply have to get the previous term and add the common difference. So we can conclude that the recursive formula is actually given as for any n, so for any nth generation, we take the previous generation and you simply add the common difference here. And that's the recursive formula that we have for the arithmetic sequence. So one last thing I want to mention about the arithmetic sequence is that arithmetic sequence talks about population. And you should understand that the population cannot be negative. So the population cannot be negative. So in case of a negative growth, so in case of negative growth, in other words, this would imply the decreasing sequence. The sequence ends at the last positive term. And everything then on is 0, 0, 0 as a constant zero value. Does that make sense? So let's go over to a little different topic in terms of the arithmetic sequence. So now we're going to talk about, before then, let's talk about a little story. So there was a really great mathematician or a physicist named Johann Carl Friedrich Gauss. Some of you may have heard of him. When he was very young, when he was in grade school, he was very brilliant. He was very smart compared to his peers. And so one day, the homeroom teacher thought that they would give him a little more challenging problem. And they gave him the problem like this. So he was to add all the numbers from 1, 2, 3, all the way up to 99, 100. Sure, nowadays we have a calculator, so we can simply add all these numbers one by one. Yes, it'll take a long time, but it's possible. And also, nowadays you can find it online as well. But back then, that wasn't a thing. So the teacher was actually expecting him to add these numbers one by one all the way up to 100, which will be very time consuming. But maybe in 5 minutes he was already done and he was already bugging other peers. So the teacher asked how he did it, and this is how he did it. So instead of adding 1 plus 2 plus 3 plus 4 all the way up to 100, which will be very time consuming, he just defined this whole sum as sum s. So it's just sum. And what he would do is he would add another sum, which is the same sum, but now in a reverse order. 98, 97, dot, 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 all the way to 2 plus 1. So we can all tell that it's the same number, but in just reverse order. And by the commutative property, we know that this sum and this sum are actually the same. So the next thing he did is he simply added the top and the bottom by columns. So what would happen? So if you add two s's, it's simply 2s. But now if you add 1 to 100, it's going to be 101. And you add 2 to 99, it's another 101. 3 to 98 is another 101. And he did all the way up to 99 plus 2 is 101, and 100 plus 1 is another 101. So you can simply see that every term now is 101. Do we all see that? So now that we have 101 for each term, and we also know that there are 100 terms in this sum, because if you're simply adding 1, 2, 3, 4, there are 100 numbers. Without writing every single number in between, it's pretty intuitive to tell. So if you're adding 101 100 times, instead of doing that one by one, you can simply write 101 multiplied by 100 because we're doing it 100 times. And if you calculate the right-hand side, it actually becomes 10,100. And this is still 2s. So this is not the answer you are to find though, because this is not the s that he wanted to find, but this is actually the 2s. So what do? You simply divide each side by 2. Then you will actually end up with s equals to, because 2's cancel out here, is 50, sorry, it's 50-50. Let me get that eraser out. So it's 5,050, and that's the answer. So when you add 1, 2, 3, all the way up to 100, this is the number you'll end up with. And you can see that this only took maybe 3 or 4 lines. But if you were to add each number one by one, that would have taken a lot longer time. So this was a very smart way to approach this. So let's talk about the arithmetic sum formula. And let's do some examples about that. So we have arithmetic sum formula. Is if P0, P1, P2 are the terms of an arithmetic sequence, then the arithmetic sum of the first n terms is given by P0, P1, all the way up to P sub n minus 1. So you should know that this is n terms, even though this is n minus 1, because now we have a 0. We're not counting from 1, we're counting from 0. So this is the n terms. And this is actually given by P0, the first term, and the last term. And you multiply by the number of terms and you're simply dividing by 2. That's all you have to do. And as you can see from this example or the story, you simply added 1 and 100, which is the first term and the last term, and you multiply by the number of terms, which is in this case 100, and you just simply divide it by 2, and there you have it. So using the formula, let's actually do a couple more examples. So actually we'll rewrite the formula for you. So here the formula is, so the sum is given by the first term and the last term, and you multiply by the number of terms and divide it by 2. So let's look at this example, which can be a little more complicated. So let's add the first 500 terms. Of the sequence where the initial population starts with 5 and you are given the common difference of 3. So this is a very different type of problem from what we saw earlier with adding from 1 to 100, because it's not going up by 1 increment. Now it's going up by 3, and we're not starting from 1, we're starting from 5. So if you're adding everything, so this will be the first term will be 5, second will be 8 because you're adding 3, the third will be 11, and it'll continue. So you're simply adding these numbers together. But how do you know the last term? Because so we're only adding 500 terms, so it's got to end somewhere. But how do you know where it ends? So it's actually quite simple, because now that we know the arithmetic sequence and the linear growth model, we can simply find the 500th term. So if the 500th term is actually 499, this is important because this starts from P0 instead of P1. If this started from P1, this would have been 500, but because the initial population starts from P0, it's simply 499, and there will be 500 terms before this. If you want to create the explicit formula, we can simply use this formula that we created earlier to find that the initial population is 5, and we're simply putting 3 for D, so it's 3n. That's all it is. So to find the 500th term, what you're doing is simply plugging in 499 in the place of n. And if you put this into a calculator, you would actually end up with 1502. So that's 1502. So this number here, the 1502, is actually the 500th term. So we can see that the last term is 1502. And just for the sake, the problem's sake, let's do one previous term, which will be 3 less from 1502. That's 1499. And so on and so forth. So there will be a lot of numbers in between, but we have managed to find out the first term and the last term, and we know that they're exactly 500 terms. So we're trying to solve this problem just as how Gauss solved it. We're going to let this equal to some number s, sum. And the next step, we're writing out the same thing in the reverse order. So instead of writing from 5, we go from 1502, we go 1499, and next will be 1496. And it's keep decreasing all the way down to 8 and 5. Oops. Eight and 5. So now we know that the top s and the s in the bottom, they're the same numbers, and we're simply adding column-wise. So if you're adding by column, you get 2s here, and we know that 5 plus 1502 is 1507, and we can also check that 8 plus 1499 is also 1507, and this is also 1507, and you're going all the way to here, which is also 1507, and lastly, this is also 1507. So we have created a new sequence that's constant at 1507, and it's not changing anything. So we know that every single term in this sum is actually 1507. And what do we also know? We also know that there are 500 terms. So we know that there are 500 of this 1507. So the right-hand side, you can simply rewrite it as 1507, and you're multiplying by 500. And this is the 2s. And let's calculate the right-hand side first. And actually, let's divide both sides by 2. Maybe that'll make the process a little easier. So that way you have s equals to 1507 multiplied by 500 over 2. And if you plug this into a calculator correctly, you will actually end up with 376,750. That's a very big number, and it would have taken a very long time for you if you were to add each number one by one, 500 times. So let's put that into the test and check this arithmetic sum formula if it actually comes out the same. So let's using the arithmetic sum formula, using the arithmetic sum formula, I'm gonna rewrite it here. So the sum has to be the first term and the last term, and you're simply multiplying that by the number of terms and dividing it by 2. So what do we have? So if you do this, we know the first term is 5, and we also found here that the last term is 1502. And you're multiplying that by the number of terms, which is 500, and you're dividing it by 2. And you'll quickly see that this addition, make sure you do this addition first because these are in parentheses. And if you add 5 to 1502, you'll actually have 1507 sorry, this is 500, and this is actually multiplication. 1507, and you have 500 terms, and you're dividing it by 2. Do we actually see that this value that we have done this is exactly same as this? So it's only logical to think that this will output the same value. So it's 376, 750. And obviously for a calculation like this, I expect you to use a calculator, but it's easy to see that this method, which clearly shows the correct answer, outputs the same number as this formula. So that's all we needed to see here. So before I let you go today, I want to do one more example, but rather more complicated problem. Let's look at an example here. So the examples that I go over during going over when I'm going over new material are a little more complicated and more elaborate problems compared to the ones that you'll see for your homework assignments. And during the next class, I will go over more examples that you're likely to see in your homework assignments. So, example. So this is a word problem. So a company will produce 30 tractors each week. For a period of 72 weeks. And place the tractors in storage at a cost of, let's say, $10. $10 per tractor per week. So this means one tractor costs $10 to store each week. So if it was for 2 weeks, it's going to be $20. And if it's for, let's say, 2 tractors, it'll be $20 per week. So the question here is how much should the company budget for storage cost over the 72-week production period. So you should really read this problem very carefully, because a lot of the times I have noticed a lot of students would think that it'll simply cost 72 times the number of tractors, but it is not, because you have to pay a certain number of money for the storage on week 1, and week 2 and week 3, and these all accumulate. It's not simply just 72nd week. So to see this problem more clearly, let's look at the, let's actually create a table. Let's do that. So let's say this is a week 1, 2, 3, 4, and all the way up to, let's say 71 and 72. I think that's enough. And the production, we know that on the first week, we have made 30 tractors because the problem tells you that you're making 30 tractors each week. On the second week, you're also making 30 tractors. So we're not adding these numbers. We're just seeing on week 1, we made 30 tractors. On week 2, we also made 30. On week 3, we made 30, 30, all the way up to the last week. And the storage cost, let's say the cost here. So on week 1, for 30 tractors that's produced, you have to pay $10 per tractor. So this would be $300 simply by 30 multiplied by $10. On second week, by now we have 60 tractors, and you can simply see that by 2 multiplied by 30, and that's 60. And on the third week, we have 3 multiplied by 30, which is 90. So that's why I created this way. So in the second week, you're simply multiplying the number of tractors, which is 60 by this time, and you're multiplying by $10. So it's going to be $600. And this is simply 60 tractors multiplied by 10. And we're going to continue all that all the way up to 72nd week. So this will be $900, $1,200, all the way up to the 71st week. You actually have $21,300, and 72nd week you have $21,600. And this number is simply found by multiplying 71 by 30 by $10. And same as this, you're finding this by multiplying 72 by 30 by 10. So here is the catch. So a lot of the students will stop here and think that this is the answer. It is not the answer. So you should really understand this table, because in the table, so $300 is how much you spent on week 1. $600 is how much you spent on week 2. So by the second week, by the end of the second week, you actually have spent $900 altogether. By the end of week 3, you actually have spent $1,800, because we're adding all these numbers together. And all the way up to 72nd week, we're simply adding all the numbers in the last row. $21,600 here is simply the money that you spent on the 72nd week. This is not taking into consideration how much you spent in the previous weeks. So please be careful when you see problems like this, and you will see problems like this. So now that we have created a new sequence, so this is a sequence, so 300, 600, 900, 1200, and so on and so forth, we're simply using the arithmetic sum formula. So the sum formula, let me rewrite it for you. the sum is the first term, oops, plus the last term, multiplied by the number of terms, and you're dividing it by 2. So in this case, so in this problem, the first term is 300. So we know that there's $300 spent on the first week. And the last term here is the $21,600. That's how much you spent on the last week, on this 72nd week. And as we can see, it's evident that there are 72 weeks. And you're simply taking the number and dividing it by 2. And if you plug this into a calculator correctly, you should end up with the number $788,400. And this is the answer that this problem is looking for. So make sure you understand the whole problem, make sure you read the whole problem, and this is not the answer. This is the answer. So I think I'm going to call it a day here, and please make sure you join the Pearson and gain access to my class. If you have any problem, please do not hesitate to reach me, and please do so in advance before it's too late. Okay, so thank you and have a great rest of the day.